Indian Institute of Technology, India. And his talk is Bio-tribology of Epoxy-based composite for hip implant application. So we are pleased to welcome Professor Shinha.
Thank you. Thank you very much, Chairman, and thanks to all of you for coming to this seminar. So, in this talk, I will talk about bio-tribology of epoxy-based composites for hip implant applications. And the motivation for this work has been that, as we know, UHMWPE has been used for quite some time. It has been very successful compared to any other material, but still it has some issues. The issues related to wear and some other issues. So therefore, many researchers have been trying to find new materials, new solutions, as well as modifying UHMWPE. So that was the motivation, and we moved towards epoxy-based, because epoxy is a thermoset, and it is quite easily available in biocompatible form, and it is already being used for some devices. So I will give you some review of what we have done in the last few years. Before that, I would like to acknowledge these individuals, my collaborators, students, and also the support from GSPS DST grant. Also, I would like to say that there is no conflict of interest, so there is no private funding to this, our research, so it's all publicly funded. Osteoarthritis is a big problem, big health problem, and in fact, some statistics show that almost 10% of the population of any country will undergo this kind of surgery, especially the statistics is from the United States, but all countries may have similar kind of result. Also, almost majority of the population will have this issue as we age. So this is a very a problem which is sort of coming because of age, as well as it is coming because of some other issues. So our joints contain articular cartilage, and articular cartilage is a very unique material, biological material that gives very low coefficient of friction, almost nearly nowhere, and but it has problem. It is not regenerative. That means if an injury comes to this cartilage, it cannot repair itself like other parts of our body which can repair itself. But articular cartilage cannot repair by themselves, so therefore the damage might remain there for a long time. And as we know, for any kind of contact situation, tribological situation, any small damage can lead to bigger damage. So that's why it is important to first resolve the issues, the medical issues, and if the issue has become too serious, then it has to be replaced by an artificial one. So artificial one, as we all know about this, the solutions of implant, and where metals, ceramics, and polymers, these three materials are used. And we are more interested in this liner material. The liner material is made of UHMWPE, and it slides against the femoral head, which is made of generally metals or ceramics, but we are more interested in metal parts. So this is our tribological interface that we are interested in. Yeah, as I said that this is a serious problem for hip and knee. We will be focusing more on the hip side because although hip and knee has a lot of similarity in terms of tribology, but there are some dissimilarities as well. So if you look at the cartilage, the articular cartilage, it has extracellular matrix, and it is very, very complex. Its complexity because of the structural strength it is required to provide, because our body weight is borne by these two joints, two hip joints and two knee joints. So that structurally they have to be very, very supportive. And they must be tribologically very supportive too. That means friction should be extremely low and wear should be nearly zero. So it's very, very complex, and I'm not going into detail about this. And the structural strength is provided by type 2 collagen, hydroxyapatite, and the lubrication is provided by glycoproteins and a host of other molecules, macromolecules. So the schematic looks something like this. For example, if it is a knee, then you can see the synovial fluid here, and two cartilages, they rub against each other basically. And if you look at the cartilages themselves, they are this kind of graded, they have graded property. That means not entire thing has the same property. So starting near the bones, which has got higher elastic modulus, better strength, and as you go to the top surface, then the elastic modulus reduces, strength reduces, but tribologically they become much more lubricious. So this kind of design the nature has produced. And this picture you might have seen, this basically tells us the complexity. So how the type 2 collagen network, lubricin, hyaluronic acid, and host of other proteins, lipids are all working here together. Okay, so this is the complexity. And other things that has been found is that these kind of molecules, they do have this kind of branching, which is also called bottle brush type of branching. So this branching basically provides sites where water molecules can attach themselves because of the hydrophilic nature. So overall they are neutral, but they have hydrophilic and hydrophobic surfaces, as well as they have charged surfaces. So because of this, they can attract water molecules and they can hold the water molecules there. So this is how the water lubrication works. And actually in the nature, water is used as a lubricant, not oil. So with this background, I would like to give you a review, because here we are talking about the materials. I would like to review what are different kinds of materials that has been used so far, and then I will present our own results. So this is the schematic, and other than wear problem, there is another problem, which is the range of motion of femoral head. That means having a good range of motion for the femoral head will lead to better stability. That means the dislocation, the chance of dislocation can be reduced if you have good range of motion. And the good range of motion can be achieved if you have a thinner line, not thicker line. Because the space in the pelvic is limited. So you can say the outer diameter is fixed. We can only play with the inner diameter, because the outer diameter is fixed by the pelvic size. The inner diameter can be increased. And how can you increase it? Unless the material has better strength, because it has to support the load as well. So therefore, a higher strength material might give you better range of motion, and therefore it will give you better stability. That means the chance of dislocation will be reduced. And obviously, either wear or dislocation, both are going to cause serious problem to the patient. So UHMWPE has been the polymer part of hip and knee prosthetic joint since 1960s. And cross-linked UHMWPEs showed improved mechanical properties. However, wear and fatigue properties deteriorated because of oxidation. And vitamin E was used in this solving this problem. And some of the samples you can see looks like this. The failed, this is from the knee. And you can see the adhesive wear, oxidation, fatigue wear. So this is the kind of failure we are talking about. And the wear will lead to wear particle formation, and the wear particles basically will migrate from the joint to some other parts. And it has been found that UHMWPE debris particles can be eaten up by macrophages, and it can create other issues in the patient. So all focus is to reduce the number of particles in the joint as much as possible. So what are material options? Of course, we have UHMWPE, cross-linked UHMWPE, and mixed with vitamin E. But in the literature, you can find that composites of UHMWPE has been tried. PEEK and its composites have been tried. Hydrogels, which is a very, very popular material, and here in this conference, we see lots of paper on hydrogels. Polymer brush drawn on hydrogel is another option. Fifth is an aromatic thermosetting copolyester that also has been tried. So all these solutions that has been tried are not clinically tried. They have been tried in the tribology lab only. So that is one thing we have to know. And then our solutions, we have tried, worked with epoxy UHMWPE composites. So let me just review some of the literature. First, composites of UHMWPE with multi-wall CNT. So in general, in the dry and lubricated conditions, so in both cases, especially in dry cases, you can see a lot of reduction in the coefficient of friction, but in the lubricated, there is not much help here. But in the case of wear, this is wear rate here, and the wear basically reduces for lubricated condition for UHMWPE with multi-wall CNT. However, increase in hardness and reduction in friction do not necessarily reduce wear rate, and these kind of specimens were found to have lots of fatigue issues. So as you make the material stronger, you run into the problem of fatigue. So this is one thing. Some other composites have been tried, and this is from our work, where we have tried nacre. So this is from the seashell, as well as single wall CNT, and also adding PFP, which is perfluoropolyether. This is in liquid form. So we basically mix them in UHMWPE in different proportions, and the results are, for example, in hardness tests in a dry condition, the hardness will be slightly better compared to pure UHMWPE, which is here. So as you add these kind of particles, basically you are going to improve the hardness. But in terms of wear, specific wear rate, we hardly got any improvement. So this is little older work, 2013, but still it is quite relevant. And we understood that making a composite like this perhaps is not helping, because UHMWPE is already very, very wear resistant, and making it further wear resistant was not possible. These pictures basically show at very high magnification how UHMWPE actually deforms plastically, and the good thing about UHMWPE is that it is very plastically deformable. It doesn't allow any cracks to grow, and that is the reason why it is so wear resistant. So conclusion from this review was that particle reinforcement of liquid lubricants such as PFP added to UHMWPE has not improved the wear resistance. Then what about fibers? So some people have tried fibers, for example carbon fiber reinforced UHMWPE. And this is the work which was done only in distilled water, but still you can see further improvement in the coefficient of friction, which is quite possible, as well as some improvement in the wear. So after adding carbon fiber, you can improve the wear rate even in the lubricated case as well as in dry case. But the wear failure is of some worrying nature. So basically wear failure happens by pull out. So carbon fiber gets pulled out from the surface, and as you can say that these kind of pulled out fibers will be very dangerous for the joint. And that's why these kind of composites may not be suitable. And as you can see, some case studies have been published where the fiber pull out was observed, and basically these joints were tried in actual patients, and basically they failed. So this is quite well-known work now. And the researchers found that the failure could have been because of poor bonding between the fiber and the matrix. So there is some scope that if we improve the bonding between the fiber and the matrix, perhaps that can help in the future. So after this, I will move to PEEK. PEEK also has been shown as a very promising material. So PEEK and its composites. So several types of, for example, this is pure PEEK and some composites, carbon fiber and graphene, as well as PTFE, and then glass fiber. So 3 different classes of PEEK composites have been tried, and in this paper, people have found that the pure PEEK has got better chance. In fact, glass fiber and PEEK composite is definitely should not be tried. It is very, very poor in terms of wear, but in the long-term test, they found that the carbon fiber with PEEK has better chance. They just show the surfaces, but the failure is still the same type, as you can see. The fiber pull out from the surface, which is again quite worrying for biomedical application like joints. And also another thing, they found that PEEK has better performance when polymer is on polymer, sliding against polymer, against itself or against UHMWPE. So in another test, another research, people have again tried PEEK against UHMWPE and against cobalt chrome molybdenum. Again, in that case, people found that PEEK against UHMWPE or cross-linked UHMWPE has got extremely low wear compared to all other conditions. However, in this research, there is a bit of conflict of interest because the people who have published this research are from the same company that has supplied PEEK. So this kind of research results should be verified. But PEEK might have some good promise if it is slid against another polymer rather than slid against against metal. So hydrogel is very, very popular, but still it is very hard to find any work where hydrogel wear has been tested. So we can see a lot of friction related results, but hardly wear results. So this is a very, very old paper now, and here also again friction results have been published. In another types of hydrogel where these bacterial cellulose was added to increase the strength. The idea is that if you increase the strength, you will have better wear resistance. And they did find that there is some improvement. So perhaps hydrogel mixed with some sort of natural fiber might be a solution in the future, but again it has to be tried. This is another work where again hydrogel was produced by 2 different methods, and it was tested. So again, we only see friction coefficient. So what I wanted to say that in hydrogel, we are yet to see wear results. Another type of solutions people have proposed is adding zwitterian polymers as boundary lubricants. So zwitterian polymers are basically polymers which are net neutral, but they do have positive and negative sides because of the sulfates. So these will again provide, just like our natural joints, it will provide lubrication because they will attract water molecules. So mixing zwitterian polymers into hydrogel, and they have observed that there is obviously coefficient of friction is reduced, and to some extent wear also improved, but I don't think the results are not enough to give us a clear path. And another paper you will find that where some aromatic thermoset copolyester has been used with multi-wall CNT. However, in this research, the conditions are not clinically relevant. That we conduct in tribology, but still there may be some solution here. So basically this is all that we can see in the literature, the kind of materials that have been used, like UHMWPE composites, PEEK, hydrogel, different types of hydrogel, and so on. So from here I will present our work, which is epoxy UHMWPE composites. So epoxy that we have used is called SU8. So this is basically a material that is used in semiconductor industry, and it is photo UV curable. So that gives us an advantage that you don't have to add any hardener. So basically in this kind of materials, the more you add things, the more toxic you will make it. So using UV curable polymer, that might help, but finally we found that UV curing was not a good idea because the mechanical property was not suitable. So we did use some of hardeners in a small quantity, but then we conducted biocompatibility test and it passed. So here basically we can see that pure SU8, which is basically epoxy, has a better strength, mechanical strength compared to UHMWPE. And the samples that we have made are SU8 with UHMWPE as part filler. So we have used UHMWPE particles as fillers, and the idea was the epoxy is obviously not a very good tribological material, so adding a little bit of UHMWPE can help to improve the tribology. And also we added HA, which is hyaluronic acid. So hyaluronic acid is natural lubricant, and therefore it will help in this whole lubrication process. So the specimens are pristine SU8, epoxy, pure UHMWPE, and these are the mixed added, UHMWPE added, for example, 25% of UHMWPE, 25% of UHMWPE, and 0.2% of HA added into it. So these are the few specimens, and before we conduct the test, it is important to know that there are some standards like ASTM F732, which gives us some conditions under which we can conduct these kind of tests. And the one very important is the multi-directional sliding, because multi-directional sliding will definitely give you higher wear rate, and this is more relevant for our joints. As you can see that in general, we will have these kind of motions: extension, flexion, adduction, abduction, and rotation. So these are the naturally we perform. Of course, this one we perform a lot during walking and running, but this maybe we don't perform so much, but you can imagine that if you are doing some exercise or just getting out of your car, you are performing adduction, okay, and rotation also. So these are the main, and basically what it gives is, in our joint, it gives multi-directional. That means one wear track will cross the other next wear track. So this is crisscross sliding in a multi-directional situation. So another thing about is we gain, and that's why it is quite complicated. So in this work we innovated by making micro holes on the specimen itself, and this part of the work was done at Kyushu University here. So basically you have this deeper the depth, and as the specimen will wear out, the depth will reduce. So by measuring the depth, you can find out the wear loss, and this is how we did. Of course, we removed the depth loss because of creep, because as long as the material is under stress, there is creep also. So finally this method gave us some way to find out wear loss without actually going through the mass loss method. First is the Vickers hardness test. So adding these fillers actually have improved the hardness to some extent, okay, in dry case, but if we soak the specimen in bovine serum for some time, the hardness actually reduces, okay. So there is a complex behavior here of this composite, the epoxy and the filler, that hardness will reduce if it is soaked in solution for some time, in bovine serum solution. When we conducted the friction test, friction measurement, we found that the 25% polyethylene with HA 0.2% gives a very good low coefficient of friction results compared to SU8. Of course, SU8 is not a very good material, but we are comparing with pure UHMWP, and it gives better result. Normally, pure UHMWP will give you results in terms of 0.14, 0.15, and here we are getting a better result. And when we conduct the wear test, again we find that 25% UHMWP particles in epoxy with HA as a lubricant has given us very better result. Well, this is coefficient friction, so compared to pure UHMWP under the same situation gives better result, and the wear also is better for this one. Pure UHMWP is not plotted here, which is somewhere here, okay, around 3.9, so this curve will come here. So in general, we have found that this epoxy SU8 plus some percentage of UHMWP and HA as a lubricant will provide a very good in terms of friction and also in terms of wear. All these results, all these tests were conducted following the ASTM standard, and long-term tests were conducted. So we have slid something like, in this, it was tested for 20 kilometers. So very long-term test. So next is another epoxy which is called Structlite. So again, Structlite was purchased from a company without any our interest. So this was, we have bought this. Structlite is also epoxy, but it is already mixed with calcium carbonate. So it behaves slightly different from normal epoxy. And here again, we have used the UHMWP particle and HA particles. And this shows that they do have calcium carbonate. So for example, calcium rich area we can see. And as you know, in tribology, calcium has a better result, a better effect in terms of friction and wear. This micrograph shows the bonding between the UHMWP particle and the matrix, and it gives a very good bonding. There is no micro cracks, and the bonding is very good. That gives good promise for wear life. And this is the sample after preparing, and this shows the surface. And in this test, we have done again multi-directional test, but on another machine which we developed. In this case, actually there is a pin. Pin is here. The pin is the polymeric part, and pin is rotating on its own axis, and the pin is actually translating. Actually, the disc, which is counterface, is translating. So there is a translation and there is a rotation. So that gives us a cross shear motion of about 270 degrees. So that means the wear tracks are always crossing each other. And this explains how it whole works. I will show you this equipment, the machine that we have. Yes. So this is the pin which is attached to a motor up there, and the pin is rotating, and the bottom part is translating. So this shows the weight, how the weight works. This is basically like a balance. There is a fulcrum, and then you apply the load there, and you get the load here. So this gives us multi-directional sliding. And the counterface was cobalt chrome molybdenum. And this pool is basically the bovine serum lubricant. So some hardness test. Again, hardness test is good indicator, but definitely not the final indicator that the tribology will be good. So all these compositions have given better hardness compared to pure UHMWP. And I will show you Structlite with UHMWP particles. About 24% has given the best result. And under bovine serum lubricated case, coefficient of friction you can see is lower even compared to pure UHMWP. Okay? And specific wear rate is also lower compared to UHMWP, pure UHMWP. So in general, this composite gives a better result. Then we added HA into it, HA as a lubricant, and with HA, in the presence of HA, we get even better result compared to without HA. So this is without HA, and so this is with HA. So this work is still under progress. For example, these data are still not verified, many repetitions. So these are only 2 repetitions. So, but we see a lot of good promise here. These optical micrographs shows the how the UHMWP particles are bonded in the matrix after the wear test, and you can see that there is hardly any removal of the particles. They are fully integrated. So I would like to summarize. Many efforts have been made towards finding a solution for hip and knee joint prosthetic implant materials, going beyond pure UHMWP or cross-linked UHMWP or even with vitamin E. PEEK against cross-linked UHMWP has shown promise but needs to be re-evaluated. PVA hydrogel and a combination with a Zwitterian polymer or some kind of polymer brush as boundary layer provides some promise. So here we can see a lot of promise here, because as we improve the mechanical property of hydrogel and we add some boundary lubricant on top surface, perhaps that will mimic the actual cartilage. And epoxy, the SU8 and Structolite with UHMWP particle and the body lubrication of HA, hyaluronic acid, can also hold some promise in the future. Of course, we have to conduct much more tests, much more study before we can be sure about this. So thank you very much for your attention. Thank you.
Thank you very much. So this presentation open for discussions. Are there any questions or comments from the audience? Yes, please.
Thank you, dear Sujit, for a wonderful presentation. I was wondering if you could expand a little bit more about the water absorption behavior of the SU8, if you have sort of more in depth looked into that.
So, well, so far all we have done is to soak it for a few days. I remember 3 to 4 days, and then conducting the hardness test. So we have found that hardness has reduced. So that is quite obvious that its mechanical property will not remain same as in the dry condition. Another thing is our tribology test has taken 4 days for each test. Okay? So to run, we have run for about 4.7 kilometers. So it took 4 days. So in the 4 days test, it has survived. And in some way where a result is an indication of its mechanical property, right? If mechanically it is disintegrating, it cannot remain the same, wear rate will rise. So if it has survived for 4 days during the test, that is another good indicator. But long-term tests we have not done. So an epoxy being hydrophilic, it will attract some water molecules, and how that will disintegrate or degrade the material, we don't know in the very long term.
Well, I was just wondering if you have measured the degree of polymerization, because most likely, like any other epoxy family or thermoset, there would be some residual monomers left around. And if the degree of you can sort of manipulate the polymerization differently to get less monomers, and which maybe would have a positive impact on water absorption. So my thought was more toward the residual monomers, if there are. Have you done those numbers on polymerization?
No, we have not done on that side. To improve the cross-linking, basically we have kept it in a mildly heated condition for a long time, for several days, like around 40 to 50 degrees centigrade. So hoping that cross-linking will be complete. But yes, I agree that there will be some monomers left around, and that will cause havoc in the material. So we need to do that.
Can I ask another question, or am I taking too much time?
Yes, please.
Thank you. So I was wondering also 0.2% of hyaluronic acid, if I remember this slide correctly, and 2% hyaluronic. For 0.2%, it was higher, more reduced of the hardness compared to 2%. Is there any logic behind it?
Actually, hyaluronic acid in its dry state, it also acts as a hardener. So actually it improves the hardness. In dry state, it will increase the hardness of epoxy. The more you add, the more hardness it increases. So, but in a lubricated case, when you have got water around, then it acts as a lubricant. So, and we found that there is some optimum percentage that gives us better tribology, because we are, after all, we are interested in tribology part. So it's not like you keep adding more and more HA and you get the good results. At some point it will come down. So the data I have presented is again limited in that case, and we need to conduct more tests to really know what is going on there.
I'll be back if there is no other questions. Thank you.
Any questions or comment? Yes, please.
Thank you for your presentation, Charlene Taylor from the BAM. I was wondering, instead of, for the PEEK material, instead of testing with the carbon fibers, do you have any chance to use other fillers or lubricant like graphite? And what would be the consequence?
You mean in PEEK material?
Yes, in PEEK material.
Yeah. As I have presented, that PEEK has been tested by some groups, but it's not that popular. Even here in this conference, I don't see any paper on PEEK. So there is some reason that PEEK has not been performing very well. And yes, we have not gone into PEEK material. So we are currently focusing on epoxy only. So I don't have any results, but I mean, adding lubricant is definitely a better idea than adding fiber, because fiber tends to have this fiber pull out, and that is not good, because it has been already tested in clinically and it failed. So as you can read in that paper that several cases it actually failed. So nobody is going to us using carbon fiber. Yeah, but lubricant is a good idea.
Okay, thank you.
Thank you.
Any short questions or comment? So I have one short question. Yes. So, for example, SU8 is harder than the article cartridge. So, which is better, harder one or softer one?
Yeah, I think in some papers you will read that people talk about stress shielding. That if you have a very harder material or very stronger material, it will cause stress shielding. But I don't think in this joint stress shielding is a problem, because joints are not parallel. They are not supporting each other. We have got load-bearing materials in series. So when you have got load-bearing materials in parallel, then you can talk about one is taking more load, the other is taking less load. Right? But here we have got the only joint is one. So stress shielding may not be a big issue. So having a stronger is no problem, as long as you have got good toughness. And again, toughness is a very, very important part, because fatigue failure is a possibility. So as you increase the strength, the toughness will go down generally. So as long as you have got a good combination of mechanical strength and toughness with good tribology, I think that should be fine. We don't have to worry about stress shielding.
Thank you. So I think there are other questions, but the time is running out. So thank you again, Professor.
Thank you.
Good.